loud. Thank you, Logan, or whoever just said that.
Huh?
Okay, so let's recap what we've done. We have solved inequalities with polynomials where we rely on the test point method, right? We apply transformations to those solutions. The final type we're looking at is solving absolute value equations and inequalities, which kind of have their own strategy and approach to it, okay? I'm gonna skip example one, just, because of time, and jump right into this theorem and then some examples. So tell me what absolute value does.
It's the upside of A.
All values in the brackets, within the brackets of positive.
Okay, so not exactly. It doesn't just make things positive, everything inside positive.
It comes from
It measures distance away from zero. So, like if you, Rachel, you were about to say, does that upside down A? It means for all. So in math notation, that just means for all, by the way. So for all real numbers and positive values A, if the absolute value of U equals A, that means U is exactly A away from zero. Well, how many numbers are exactly U away, or exactly A away from zero?
A, negative A.
2. A itself and the negative of A are exactly that distance away from zero. So in other words, every time you have isolated an absolute value and you have the absolute value of something, even if there's more than one term in there, equals a specific number, then you're always going to have these two solutions. Either it equals the positive of that, exactly 3-way in the positive direction, or exactly 3-way in the negative direction. So the setup, and you guys, this isn't new for you. You've seen problems like this probably last year, but we'll review absolute value equations and then jump into the inequalities, which are going to be a little more complicated. Okay, is this too dark? There's a light. What's that?
You can see it fine.
Okay. Okay. All right, so if the absolute value of x plus 5, that does not mean x is 3 away from 0. It means x plus 5 is 3 away from 0. So that's going to give you two possible answers. Either x plus 5 equals exactly 3, or the only other number that's 3 away, x plus 5 equals negative 3. And then you just solve both of those situations. So these absolute values are basically breaking up into two different possibilities, two different solutions, if you're looking at an absolute value equation. So we've got two solutions, x equals negative 2, or x equals negative 3 minus 5, which is negative 8. So notice, while we're used to absolute values being like, oh, it just makes it positive, or I have two possible answers, 3 and negative 3, because you have other terms inside, your values are not just going to be opposites of each other. You have to go through the process of solving each of those. So we've got two possible solutions, 8 and negative 2. It also said, or negative 8 and negative 2. If we're graphing on a number line, that's all I'm looking for. The number lines will make more sense when we're doing inequalities, by the way. Okay. All right, so the next, 3x minus 2 equals, actually, let's skip that one. Let's go down to C. The absolute value of x squared minus 9 equals 7. So that means x squared minus 9 itself equals what? 7 or negative 7. So set up your two equations first. X squared minus 9 equals 7, or x squared minus 9 equals negative 7. Now we have two equations. Focus on them one at a time. So let's just focus on the one on the left. My solution is x squared, add 9 to both sides. So what's my solution for x? 4. 4 or negative 4. If you take the square root of both sides, you have to account for the negative root. That could also be a solution for x. Okay, let's solve the second equation. Add 9. Negative 7 plus 9. Solutions for x. or the square root of 2 or the negative square root of 2. So every time, again, you take that square root, you have to account for the possibility of it being the negative root as well. So how many solutions do I have here? 4. We are used to having 2 solutions with a quadratic, but a quadratic inside an absolute value will produce 4 possible solutions. So on a number line, we're looking at -4, negative root 2, positive root 2, positive 4. So we have these 4 possible numbers that when we plug in. Now, and you should be able to check this even with mental math really quickly, like, oh, does negative root 2 really work? Well, when you plug negative root 2 in for x here and square it, you get positive 2. Subtract 9, negative 2, or negative 7, square root of or absolute value of negative 7 is 7. So you can mentally check those pretty quickly. Okay, any questions on this? On absolute value equations, you basically just always isolate the absolute value first. These are all isolated, by the way. Like if I had something else out front of here, like a 5, first you would need to divide both sides and just get the absolute value by itself. And then you just break it up into your 2 possible solutions. Okay, cool. All right, now let's look at inequalities. Make sure you're still thinking about what absolute value means, because the more deeply you understand what absolute value means with respect to something related to 0, the easier time you'll have with setting up inequalities. So we're going to focus on the absolute value of something being less than a number first. So you notice every single one of these examples is less than, less than, less than, because whether it's greater than or less than will change the setup of the problem. So let's just think about a number. I'm gonna not use the u and a. I'm just gonna stick with x for a second. The absolute value of x, like if I said the absolute value of x is less than 3. Tell me about possible solutions for x right now. It's not just 3 and negative 3 anymore, right? Anything greater than 0, so if this was 0 and this was 3, anything greater than 0 and less than 3 has an absolute value of less than 3, but there's more. And greater than negative 3. So it's basically not just those 2 boundary points, negative 3 and positive 3, but everything in between too, because everything in between still has a distance of at least less than 3. Does that make sense? So when you have an absolute value and it's less than a value, less than a specific number, you can first replace it with an equal sign. You've got your boundary, you've got 15 and negative 15. But if we're talking about distance from 0 and it's less than 15 units away, then it can be anything in between negative 15 to positive 15. So how do we write that out mathematically? So in this first example of x, if the absolute value, distance from 0 of x minus 7 is less than 15, then it could be literally anything. X minus 7 could be anything between negative 15 and positive 15. So how do we set that up? That's with a double inequality. You guys will like this. These are fun problems. You set it up with a double inequality. So x minus 7 itself, I said, was in between what 2 numbers? So it's greater than negative 15, but less than positive 15. So we have set up this double inequality. And I want to figure out, right now, we kind of like have this solution for x minus 7. I just want my solution for x. Add 7 to all sides or all parts. So we're used to with like 2 sides of an equal sign. With this, you're adding 7. We want to get x by itself, but we add 7 to every piece of this double inequality. So that will leave us with x by itself in the center, which is then always greater than negative 15 plus 7. So negative 8. And less than 15 plus 7, 22. So any number between negative 8 and 22, when I subtract 7 from it, it is within 15 units of 0. Is basically what that means. So this is our solution. Represented on a number line would be, I would have -8 and 22. Open or closed circles. Open circles because it's strictly less than. And then everything in between that is a solution. So notice 15 isn't an actual value in our solution because of this extra -7 here with x changes those boundary points. So far, so good. Okay, let's jump to C. 2x plus 3. The absolute value of 2x plus 3 is less than 5. So 2x plus 3, that whole chunk of stuff is no more than 5 away from 0. So what's my double inequality going to be? -5 is less than 2x plus 3. Okay, so we need to switch those. No, that's right, you're right. Which is less than +5. Good. So the whatever's inside the absolute value is wedged between somewhere within the window of -5 to +5. So you set it up first and then start undoing whatever's happening to x. So first we will subtract 3 from every piece of this. Subtract 3 from -5, subtract 3 from 2x plus 3, and subtract 3 from +5. We end up with -8 is less than 2x is less than 2. You can also divide every single piece by 2. So divide by 2, divide by 2, divide by 2. And we end up with a solution of -4 is less than x, which is less than 1. On a number line, -4 to 1. Everything in between, open circles on the boundary points because it was strictly less than 5. So far, so good. Okay. Let's do D because it looks a little different because we have a fraction in there. So again, I just want to reiterate that for every single one of these, we are given an absolute value of an expression is less than a value. So an absolute value, distance from 0 being less than a number means you're stuck within a window. So for this one, what are my boundary points on my beginning boundaries for my double inequality? -2 and 2. X over 7 plus 9 is wedged between those two values. First subtract 9, so it'll be -11 is less than x over 7 is less than 2 minus 9, so -7. Multiply, yeah. So now we're multiplying every piece by 7. So we end up with a solution -77 is less than x is less than -49. And that should still make sense. Like those numbers should still be least to greatest, making sense. So our solutions are between those two values, -77 to -49. It was strictly less than again, so everything in between with the open circles. So far, so good. Okay, so now let's switch. So these were all the same setup because they were all less than or equal to a value. So what if the absolute value of something is greater than a number? So I'm going to go back to like our example of 3. If the absolute value of x is greater than 3. So think distance from 0 every time you see absolute value. I would, like in my head, I replace it with distance from 0 is greater than 3. So visualize what that would mean on a number line if this was 3. Tell me about possible values of x. If its distance from 0 was more than 3 away. negative infinity to negative 3, and 3 to infinity. So my possible values of x, instead of being wedged between negative 3 and 3, there's like a window, a gap where it can't be within that in between value now, negative 3 to 3, and it's on the outside of it. So my possible solutions would be everything up to negative 3, nothing in between negative 3 and 3, because that distance from 0 is less than 3, and then everything after it. So it's like the reverse of when the absolute value of something is less than, it's between. If it's farther away from 0 than a number, you've got those two outside possibilities. So this is no longer a double inequality because there's no such thing as a number that is both greater than 3 and less than negative 3 at the same time. So these problems will be set up with an or, like either it's less than this value or it's more than that value. So you'll have two separate inequalities with it. So let's just jump straight to B. So we've got the absolute value of 4x minus 5 is greater than 1, meaning the whole chunk of 4x minus 5 is farther than 1 unit away from 0. So that gives me two possible options. And if you need to visualize the number line, do it. So if I've got 1 and negative 1, 4x minus 5 has to be over here or less than negative 1. But that's 4x minus 5, not x itself. So you just have to figure out what x itself would be. So you're going to set up your two inequalities. So you would have 4x minus 5 is either greater than positive 1. Notice that that follows the exact setup of the equation or the inequality, greater than 1. 4x minus 5 is greater than 1. Or 4x minus 5 is less than negative 1. So you switch the sign and negate it. It's either greater than the positive value or less than the negative. And then you're just going to solve each of these separately, as opposed to with the double inequality, we could solve it all at the same time. So add 5. So just focus on 1. I'm focusing on the one on the left. Add 5, you have 4x is greater than 6. Divide by 4. X is greater than 6/4, which is greater than 3/2. So that's 1/2 of my solution. So the other one, now I'm adding 5 to negative 1, which is 4, divide by 4, and I get x is less than 1. Now, when I graph these, it's kind of like a good check because visually I should have like this open gap on the number line for solutions, because when this is greater than, you have this window of stuff that it can never be. So when you graph this, x is less than 1, and 3/2 is 1.5. So it still does create this gap. So 1.5. So your possible solutions are everything on the outside of that. Questions on that one? So in math 3, what we would do is we had problems just like this, but we didn't think about it as deeply conceptually with distance from 0. What we would do is find the boundary points, and then you guys just had to test values to see which part of the number line made it true. In this case, instead of testing values, we will go through the process algebraically to actually solve for the values rather than testing values. Okay, let's look at a couple more. There's definitely one that I really wanted to do. It was C. Okay. All right, the absolute value of x squared minus 5 is greater than 6. So the distance of x squared minus 5 from that to 0 is more than 6. So what are my two inequalities? X squared minus 5x is greater than 6.
Or x squared minus 5x
Or x squared minus 5x is less than what? Nope. -6. Yeah, so visualize that window. 6, -6. Visualize the number line. Okay, now I've got 2 inequalities to solve. How do I, again, focus on one at a time. So let's just look at x squared minus 5x is greater than 6. How am I going to solve that? Factoring x out would help only if this was actually a 0 on the right. So make it 0, he says. How do I make it 0? Subtract 6, and now I have a quadratic. Okay, factor. Yeah, so what multiplies to -6 adds to +5? That's going to be multiplies to -6. That would be -6 and +1. Okay, I have an inequality with 2 factors. We have a strategy for that. Set it equal to 0. Test points. So test point method here. Don't forget about that. You're going to need it. Test point method. Okay. All right. So my 2 zeros. Find the zeros. 6 and -1. And -1, 6. And then we just need to test some values. So let's test 0 for the in between. 0, -6 times +1. So we're multiplying a negative times a positive. That's a negative. Pick a number less than -1. -1,000 minus 6 is still negative. Add 1, still negative. Multiply that together. Your product is positive. Something greater than 6. 1 million minus 6, still positive. Plus 1, positive. Product, positive. Okay. We wanted the solution for when this whole thing was greater than 0. So I've got 2 pieces to that. It's everything up to -1, right? So I need to get organized. We'll probably skip part D. So I'm just going to keep writing down here. So -infinity to -1 and 6 to infinity. Okay, that's only part of my solution. So we did all that for the one scenario where our quadratic was greater than 6. Now we have when it's less than -6. So how are we going to do that? Add 6, same thing. Add 6, get the quadratic on one side, factor. So we've got x squared minus 5x plus 6 is less than 0. Make sure you're keeping track of your inequalities and using the correct one. All right, now while it looks very similar, we still have a 5 and 6 in there. It's not going to factor in the exact same way. So in this one, we're looking for 2 numbers that multiply to +6 and add to -5. So yeah, not 6 and 1 like the other one. We've got -3 and -2, add to -5, but have a product of +6. So x minus 3, x minus 2, less than 0. Now what? Test point method. I've got my zeros, 3 and 2. And now I test. Okay, a number less than 2. 0. That would be a -3 times -2, which gives me a positive result. Okay, this one you will have to use your brain a little bit. Between 2 and 3, 2.5. So when you subtract 3 from 2.5, you get a negative. But when you subtract 2 from 2.5, you get a positive. So that's a negative times a positive, which has a negative product, and then something greater than 3,
1 million.
1 million. You're gonna have a positive number times a positive number, which has a positive product. Okay, so this half of it, we were solving for when this quadratic was less than 0. So we have between 2 and 3. So the final solution here is the union, the combination, or not the combination, not the overlap, but the union, including means all of these together on a number line. So if you think of it, so we've got everything up to -1, then we jump to everything between 2 and 3, then everything from 6 to infinity. So when we represent that solution visually, we've got several boundary points on our number line. We've got -1, then I have 2, 3, and 6. And so the solution was everything less than -1, open circles, nothing between -1 and 2, between 2 and 3, and then everything after 6. So that visually represents all the possible values of x that I could plug in here, and that absolute value would be greater than 6. Isn't that interesting?
Super.
Doesn't it just, was it a little bit fun to put that on a number line?
A little bit.
Yeah, a little bit.
A little bit.
Okay,
Could we do
all
it
right.
again?
What?
Could we do it again?
You want to do another one? Okay, so we're gonna skip D, but it's the same thing. You do have those two separate. Anytime you have absolute value with a greater than, you've got the two separate situations. If it's less than, you've got the double inequalities. So moving on. Now we will be able to represent certain like real world scenarios in different ways, and one of those ways is going to be absolute values, any absolute value inequality. So this is a timely problem. So a pole percent is within 5% of the true percent. So poles are not 100% accurate. You know that. It's like we use a small sample to guess the outcome of a huge population. So a pole percent is always within a certain, they guess it's a certain, within a certain percentage of accuracy. And in this case, it's within 5% of the true percent. The poll shows that a candidate has a 48% of the vote, but it's got 5% wiggle room on both sides of that. So that's a huge window of like, I think we would call it deviate, like it could deviate a total of 10%, right? That's a lot. So we're gonna represent it with an interval notation, which we're familiar with, double inequality, which we're familiar with, an absolute value inequality, which is new, but they're all going to be representing the same thing. So like I said, if we're talking about, we got a poll result of 48%, 48% of the population is in favor of a certain candidate, but there's a 5% window of possible variance, I guess. So what's the lowest percent, the true percent that it could be? Huh? 43, 5 less than 48. What's the most it could be? 53. So in interval notation, we're just talking about 43, 53. That's it. So that's how we represent that true percent. If we're using absolute or interval notation, should we use brackets or, let's see, it says it's within 5%. I guess I always thought that would be a bracket. I've always used a bracket on that. Because if it's 43, it is 5. I would argue bracket, just because it is still 5 away. 43, 53. Okay, so this is not new for us. That makes sense, right? How would we represent the true vote with a double inequality?
43.
Here, the values P, the possible values of P itself. So we'll use P. Yep. P is greater than 43 less than 53. So it means the same thing, less than or equal to. How could we represent it with a absolute value inequality? So this one's a little tricky because you got to think about what goes inside the absolute value, what's going outside of the absolute value. My strategy is I think of like that difference. They want it to be no more than 5% away, right? So that's when I start visualizing the absolute value of something is no more than 5% away. So that tells me, okay, the difference between two things, it's going to be within 5%, right? Less than or equal to 5% away. And then, go ahead.
Is it X? Is it, I mean, P plus 48?
Close. The difference between
P
the
minus-
actual percentage and the
oh, so
whole
P minus 48.
P minus 48. So what that means is the difference between the actual percentage and the polled percentage has to be 5. Now, could you have said 48 minus P?
Yes, that would be different.
Right, but we're taking the absolute value, right? The difference between 48 and the actual percent needs to be less than 5. Let's plug in a number. Let's say it was 50. So if I did
Oh, I guess not.
50 minus 48 versus 48 minus 50, yeah, that matters unless they're both going to come up to be 2. So both of these are correct. Doesn't matter. That's what that absolute value is allowing you to go in either direction 5. Yeah, neat. Okay. All right. One more. So you guys are going to get some problems on the test where you can use a graph to solve problems. So in a problem like this, the graph 3x minus 2, find where it equals 4. So you could think of it algebraically. When does 3x minus 2 equal 4? And you could go through it algebraically. If I say use your calculator or use any method to solve, you could also put it on a graph this side into your y1, graph this side into your y2, and then you could also just visually see where it's going. So I'm going to real quick. This has a vertex at 1/2, this absolute value. This is not going to be super accurate because I want to rush through it, but if that's my absolute value, how do I graph the 4?
Just go to Y equals 4.
It's a horizontal line of 4. So if you're looking at a graph trying to figure out where one function is, my spacing got weird here. If I want to know where my function is greater than 4, you're literally looking at when those y values are greater than 4. Like in this case, it would be the absolute value is greater than 4 there. So you figure out which x values that's happening for. If I was asking for when it was less than 4, you're looking for when those y values are less than 4, and your solution would be that x interval where that's happening. So while we have these like specific strategies for solving based on absolute value less than, absolute value greater than, it's still important to understand what's happening visually when we're solving these problems. We're checking to see when an absolute value graph is higher than or lower than a certain number. Does that make sense? Okay. All right, we're going to stop there. So you've got your 310 worksheet, and I'll collect that next time. And then we're done. Oh yeah, we do.
When is town meeting?
Right now.